Hello, hello. Today we're going to be going over like Newton's laws of motion and kind of just forces in general. Relatively basic problems. What I got in front of me, it's currently a blank page, but I got a bunch of questions and the subsequent, the respective answers. So we're going to go through a few of them, just kind of at random, honestly. But before we do that, I want to go over a few quick concepts to make sure we're all on the same page. So let's do just that. So, as I was talking about, the is the topic is Newton's laws of motion. So that would be our topic. Add a little color, I guess, and let's go into it. So the first thing we're going to define is inertia. That is the tendency of an object to remain at rest or move with a constant velocity. I'll try to squeeze it in. Okay, so keywords here, we got rest, we got constant velocity. So if it's at rest, we can say that both the velocity and the acceleration are zero. And if it's at a constant velocity, we can say that the acceleration is zero. So it's kind of, tendency to resist a force, resist then an acceleration with that. And what we can say is that mass is a measure of inertia. So, kilograms. That'd be an example. Now we have inertia defined. Let's move on to Newton's first law. Okay, so Newton's first law states that an object will remain at rest or move with a constant velocity unless, it's not an N, unless acted upon by an external, now this is the key word here, unbalanced force. So let's say we have an object, it's at rest. It's just, easier way to pick things. And it's acted upon by a force going right of, say, 70 newtons. Doesn't really matter. That is an unbalanced force, and that is external. Now, let's say we have another force going 70 newtons, of 70 newtons in this direction. So our net force is actually zero. In other words, it's balanced. So like this would be balanced, and though it's external, there is no net force, and it will remain at rest. There will be no acceleration and no subsequent velocity. So let's talk about Newton's second law. Okay. So Newton's second law, we have a force acting upon an object. Let's draw a little diagram here. And what we can say is that the acceleration of an object is directly proportional to, trying to switch colors there. Okay. To the net force on the object, and inversely proportional to the mass of the object. Now let's generate a few ideas from this and say that our acceleration of the object is directly proportional to the net force. If something's directly proportional, when it increases, say the acceleration increases, or more accurately, we would say the other way around. So let's say the net force increases, then the acceleration would increase. The way we do that is simply the summation of the forces, i.e. the net force, and that will be our directly proportional. Now, our inversely proportional means that as our mass of the object increases, the acceleration would decrease. And the easy way to do that would be division. So over m. And with this, we get one of the most important formulas, which is F net equals ma. And just want to relate these two. That's the same thing. Okay. And just note that force is measured in newtons, but that should be fine. Now, Newton's third law. So, Newton's third law. For every action, there is an equal and opposite reaction. Now, this we can substitute even the word action for force, reaction for force as well. So if you think about, a box on a surface, what we're going to have, say the box is of mass equals, I'm going to delete that error, just confusing. The mass is equal to 50 kilograms, something like that. Now, we have our force of gravity acting downwards, as well as our contact force acting upwards. So because we have this gravitational force acting downwards on the box, that is our action. Now there's going to be an equal and opposite reaction, and from that we can actually say, this would be mg, this would be F sub n, our contact force, and we can say that mg is equal to F sub n, because it's the only two forces in the equation, and they're opposing, and they're equal. So that is also a very important force. A very important law. Okay, so what I'm going to do, I want to keep this video short, so I might split it up into different ones. But now we have went over our concepts. Now let's go into the problems. So just for the first one, we'll go through a few of them, just whatever tickles our fancy. We have a weight of the pumpkin in newtons. So in order to transfer it into newtons, all we have to do is just 14 times 9.8. So the gravitational, the force of gravity, the acceleration of gravity on Earth. And that will yield us 137.2 newtons. Now, what is meant by a net or unbalanced force? I'm not going to write this one, but if we have a net force, or an unbalanced force, essentially what we have is, maybe we have a vector going this way and a smaller vector going this way. The net force is going to be this way in the direction of the bigger vector because you just do some subtraction. And what you see is that this is, again, our net force, and it's unbalanced. So we have essentially, you can imagine someone like pushing a box that way. What direction is going to travel? Well, it's going to travel to the right. It's going to have an acceleration. It's going to have a velocity now, all because we have a net unbalanced force. Now, if your net force is 0, it's not going to move, but I think they want you to think it's unbalanced. Now, if an object is at rest, there are no forces acting on it. Is this statement correct? No, that would not be correct. I mean, it could be true, but the use of must makes it, incorrect. If forces are balanced, then no. Yeah, I mean, if forces are balanced, then the object can still be at rest. And so for part B, if the net force on the object is 0, can you conclude that the object is at rest? So the net force, okay, this one we're going to go to our Newton's third law and say F is equal to ma. Now we can, from this B, we can say that, this force is equal to 0, which is m over a, which means that the acceleration is equal to 0. I'm not including units because of the space, but that's meters per second squared. So the acceleration is equal to 0, but one thing we have to note is that it can already be moving at a velocity. So what we can say is that we can conclude that the object is at rest / a constant velocity. In other words, its velocity isn't changing, because if there's no net force, there's no acceleration, but that's all we can say. Now, let's do a problem. Okay, quickly we'll look at 5. So consider a 2-kilogram ball and a 6-kilogram ball in free fall. What is the force acting on each? So on both we have gravity, and we would just do 2 times 9.8 and 6 times 9.8 to get those values. I'm not going to calculate them. And the acceleration on each, what we know is that the mass of the ball doesn't actually influence the acceleration. It's going to be a constant 9.8 because of gravity. That is the answer there. So let's try 6. So it's not too bad. So I'm going to go copy this and bring it down. Oh, kind of dropped that. Okay. Just going to scroll down and paste. Cool. So this is our problem. Let us find out the answer, shall we? So we have a 5. I know there is like a drawing here, but it's kind of like tough to see it, so I'm going to redraw it. We have a box, and that was 4, but we have a box. Mass equals, and we won't say the m, it's just kind of messing up here. 5 kilograms. It's frictionless, so mu equals 0. And it's acting by forces F1 and F2. So we can kind of see that there is a downward force acting on the box at an angle 30 degrees. This is F1, I think. So that would be 5.5 newtons. And then we have a force going this way. That would be F2, so that's 3.5 newtons. And this is at an angle, I think that's 37 degrees. So now let's go back to the problem actually and see what are we even trying to find now that we understand everything. I'll just draw a floor too. So it says what additional force, oh, that's an eraser. What additional force will keep the block at rest? So it's already at rest, so that's okay. We don't need a deacceleration. All we need is to prevent acceleration. So what we're going to see is that there are forces, they're both acting in this direction, so we're going to have a net force in the same direction to the right. What we want to do is calculate that net force and then say, okay, well, in order to keep it at rest, in order to have a balanced force, what we need to do is just have the same thing in the opposite direction. Then they will cancel out and be 0. So what we got to do is break these up into components. So what I'm going to do is I'm going to say F1, and I'm going to vectorize these and break them up to components. So we have on our X, we're going to have 5.5. Let me just highlight this, what I'm trying to do. So we're trying to find this component right now. So it's going to be 5.5 using our rules of trigonometry. We're going to have, this is the opposite side, but this is the adjacent side. So we're going to use cosine. Cosine, 30 degrees. And then we'll also include the y component. So we'll say 5.5, and then we're just going to use the other one because it's opposite, which is sine 30 degrees. Cool. Now we're also going to put F2. and that's going to be 3.5. Also, actually, I messed up. What I forgot to note is the direction. That's my bad. So what we have to keep in mind is where is everything going, actually. So what we have is essentially this force is going to be downwards and to the right. And down is negative, so we have to include a negative sign there. Now, before we even get to the other problem, let's just see what it is going to be. So it's going to move upwards, and it's going to move to the right. So positive and positive. So we're safe over there. Messed up on that one, though. Luckily, we caught it. So we're going to do 3.5 cosine 37 degrees. Then we're going to do 3.5 sine 37 degrees. Now we're going to add those up, have our resultant force. But before we do that, I'm going to show like an alternate way to think about it. It's the same concepts though. So we can have our force 1 along the x, force 1 x, just say that. And that's going to be equal to our magnitude and times our cosine, or times our angle, cosine of our data. And that's actually going to be the same thing we wrote over there. This is an alternative way to like piece it together. So we can actually say, we're going to actually backtrack a sec and say that the summation, nope, screwed that up. The summation of the forces on the x is equal to F1x plus F2x. Then we say that F1x is equal to this, F2x is equal to 3.5 cosine 37, and then from that we can easily come to the conclusion of, I guess I call it F net x, which would be F1x plus F2x. And we could do the same thing for y, clearly. So I prefer this, this vector notation. So that's what I'm going to be rolling with. But yeah. So I'm plugging into the calculator right now. Make sure you're in degree mode. And I'm plugging it in. Okay, so I got a 7.558. And then for this one, we have, second, a negative 6.4. Nope, that would be a lie. 0.64. 0.644, we can say. Okay, so that are the components of a resultant vector. Essentially, we can determine that we have a force to the right and down a slight amount. So essentially, I'm just going to draw an arrow over this for 1 second. We got a force, I think slightly downwards. So it's kind of going like, it's not going to go into the floor, but that's kind of where the force is headed. Now, again, what we need to see is what additional force will keep the block at rest. So what we're going to want is actually, looking at the answer key actually, apparently they left it in this component form, but I will write it alternatively just because. So what we're going to want is the magnitude of this, so I'm just going to say extra. We want the magnitude of this, so we say FR, that's a resultant force. Magnitude of it, oh yeah, I guess I kind of forgot the arrows. Sometimes a little too lax with the notation. And this is equal to the square root of 7.558 squared plus negative 0.644 squared. And I'm going to plug that in. Okay, so the result for that would be 7.585, which is close to the x because that's the main force there. the larger part. Now what we're also going to do is find the angle. We're going to say that theta is equal to the tangent inverse, or arctan, of our v, it would be vy over vx. Yeah, I don't want to mess that up, but I believe that's correct. We can see if it makes sense at the end. And actually, I mean, technically it would be like force. Don't want to confuse anyone. So then we're gonna go and plug that in. Now, the one thing I like to do, and the one thing you should do, is first you take the absolute value of this and plug it into tangent, and only then afterwards do you consider the signs. So what we know is that we have a positive and a negative. So essentially it's going to be below this x-axis, and it's going to be, alternatively, you can write, well, I mean, we're going to write this some degree underneath the x-axis or below the x-axis. It turns out it's 4.87 degrees below the axis. So actually we have a force of this is our, okay. Getting a little tired, so I'm thinking a little slow, but I got the ideas. So our resultant force is going to be 7.585 newtons at 4.87 degrees below axis. Now this isn't our answer, so we need, I'm just going to call it like the counter force. Probably not the best name, but who cares? And what we're going to want is to essentially flip this. So I'm going to do a little graph, and our pink thing is going to be the force of our resultant force. And the way we're going to counteract that is simply like flip it, essentially. Or I guess more accurately, like rotate, because if you flip it along the x, it would, or flip it along the y, it would just be that. I don't know why all those messages are coming now, but there we go. And so essentially we want that. So what we can see is that this is going to be a positive angle, and it's going to be, yeah, essentially it's going to be, here, we're going to have, how do you want to say this? I guess what we can say, 7.585 newtons. I'm a little lazy, so we're just going to refer to this as our, our northwest. 7.585 newtons northwest at, I guess, just 4.87 degrees. Kind of a lazy way of doing it, so I'm actually going to change that. I don't like that. We're going to say 7.85 newtons, so we know that this angle right here, these are equal, just some geometry, 4.87. So what we can do is 180 minus 4.87, which would simply be, don't want to mess it up, 175.13. So our angle of this resultant force would be at 175 degrees above the axis. It's like a way of writing it, but it does convey the idea. Sometimes I mix how you should do it in math and how you should do it in physics, but it should be acceptable at the very least. You get the idea. So that's going to be this problem, and that took much longer than I anticipated. So we're going to end this video here, and we're going to come back in a second.